somewhat. Okay, see, now a natural sequel to motion in regular wave would be motion in irregular wave. So, although I am going to call this ship motion in irregular waves, I will still pick up little bit on the regular waves part and continue. See, again, motion in irregular wave obviously should follow from the study of motion in regular waves. So, in fact, we have to continue a little bit on motion in regular waves because some of these parts are very crucial in order to study irregular wave part. So, I will still continue some small discussion on regular wave motion in regular wave. Okay. What I will do? See, let us talk about some simple thing of natural period. Why it is important now? Natural period is turns out to be equal to, for in heave, equal to rho g a. I am just writing the formula AWP by mass plus added mass. This is the formula. Okay. Now, if you take a typical ship, in fact, we can work it out various ways, but if you take a typical ship value, let me work it out here. Rho g AWP is actually L into B into water plane area coefficient. Okay. Mass plus added mass can be written as 1 plus Ca into mass. Mass is rho into Cb into Lb into T, root over of that. See, I am just breaking it down just for benefit. Cb into length, breadth, draft into rho gives you mass into 1 plus added mass coefficient give you this. This is rho into G. AWB is LB, Cp. So, if you do that, cut this, if you cut that, then rho gets off, then it becomes proportional to G by 1 plus Ca, G by 1 plus Ca, Cwp by Cb. Okay. I think now there is T there, G, Cwp, T will be there. Now, if you work it out for a typical shape, you will find that this is almost like a 1. See, this will be almost like a 1. Now, T, let us say Ca is actually also 1, so it is 2. Okay, let us say it is 1, so it is 2. So 10 by, let us say 10 by, it is 10. So you can say if you take G to be 10, 9.8, approximately 10, 1 plus Ca to be 2, this it becomes 5. So it is 5 by T, root over of 5 by T. You take any T value, say T of 8 meter or something. So root over of 5 by 8. If you do that, that frequency will come out to 0.8 or so. 2 pi by 0.8 if you do, period, see this will turn out to say say 0.81 like that, maybe less also, maybe I will put it at 0.6 to say 1. That is, remember frequency, 2 pi omega e. What is T? 2 pi by omega. 2 pi by 0.6, how much? It is 10, 12. So T turns out therefore, natural period of heave is in order of 8 to 12 seconds, something like that. I mean, it is not really away from the typical wave frequencies. Every day the wave you find is that order. So, you see, here becomes a real problem. In other words, what I am saying is that supposing it happened that you are forcing frequency waves were of a period which is very far from the typical natural period, you would not bother. It will never resonate. So, why care? But it happens it is not so. Another thing you will find that here it is inversely proportional to T. Opposite of T, you can see from here. So, if a ship is shallow, as would happen to a barge, you would have here a high frequency, low period, 10, 6 second, 8 second like that, which happens to a small boats normally. On the other hand, if you have a deeper ship, it has a low period. So, if area of water plane is very large, this is high, then you have a obviously high frequency, low period. Now, that would happen to the barges that that goes from Calcutta, that Howrah to that one, this large water plane area, small depth. You should never take them to sea. It's going to go up and down like a cork. Okay, very bad. So this is one point to note that the kind of range. Because later on we will see that in a spectrum we will find out in an irregular sea which one is occurring most, and you must try to have a ship design if the natural period is not close to that. I want to just briefly talk about roll here. Roll natural period T, not T, omega roll, it becomes equal to rho g into uh, volume into GMT, actually just like there it was rho g into AWP into Z, this becomes actually this way, and here it becomes your moment of inertia I Z Z into 1 plus that factor, that say that moment of inertia factor, something like that. So never mind this writing. What I want to tell you is that this depends inversely, this thing with GMT. You see, if GMT is increased, roll period is increased, roll frequency is increased, period is decreased. So you see period T roll increases as GMT decreases, and it decreases as this increases. That means if you have a smaller GMT, that metacentric height, you have a larger roll period, lower frequency, larger period. You will find out again if you do that, typically this number will come to be around 8-10 seconds or something like that. If you make GMT very high, you will see it will come to 6 seconds. If you make a GMT smaller, it will say maybe half a meter, it may come out to be 15 seconds. This is where the contradiction comes in. A vessel which is having GMT high, this is called a stiff ship. Very stable but stiff. So stable, it makes sense. You see, you have, let us say the ship is tilted by 10 degree. Its GM is so high that the restoring force is very far, quickly bring it back. Okay. Where the restoring force was small means it will be brought back slowly. So you see, safety requires that you must have high GMT, but high GMT makes it more uncomfortable. So you have to have a compromise in a vessel. Now why roll it is more important. Now you take an example. Suppose I take a semicircle. This is my last thing on this regular wave. Now I rotate it. What would happen? See this water particle, they will simply, it will be like a butter, the vessel simply will go up and down. What kind of wave you think it will make? Practically no wave, because it is, you see it's a circle, so it is like a groove is there. So you are, supposing I pushed it down, then the particle got pushed down, but here I am rotating it, remember, like a cylinder. So when I am rotating it, there may be some surface stresses, they are very small, which we are neglecting, but the net pushing of water is just not there. It is, you can say that I made a cutting in the water and the thing is going. That is why the roll damping is very low. There is no roll damping. Therefore, if roll damping, that is B roll, is very low, you don't expect any, like this sort of in a resonance, lower motion, it is very high. So that's why you have got, if you don't have anything, you have, of course, normal ship will have some damping because it is something like that. But I am saying still it is much lower when you rotate that, the damping, the wave mechanism is much lower. This is why when you take a model and if you just tilt it, for a long time it will actually oscillate. You can take yourself, you take a bucket and anything that float and you tilt it, it will for a long time go. But you push it down, it will go to and stop. You take, next time you tank, if you go, you just take a body and push it down, it will just go twice and stop. You roll it, it will go for a long time. Why? Because there is nothing stopping it, no damping. So what you do, you put bilge kiln. You put all kind of stuff, anti-rolling device. This is why you put that. Because rolling, first of all, it is, dangerous. Large rolling means it can be dangerous. And on the other hand, you don't have a natural damping mechanism. So you have to induce mechanism by putting bilge kiln. So that you don't get. See, you may not change the frequency. Remember, you cannot change the natural period is say 12 seconds. You cannot change it, but you can, at 12 seconds there is no damping, it would have gone to 30 degrees. If you put a damping, it will go to 10 degrees. So you have to put is damping. This is the mechanism. Second, another thing that is most interesting thing I want to show you about this thing is this thing. If supposing restoring force is very important, then the ship will always be actually following the, like this. I was telling you the two extreme, when the restoring force dominating and when the inertia force dominating. When restoring force dominate, that is restoring force, that is hydrostatic, you can say hydrostatic force dominating. Then typically what happens, it actually follows, I am showing a beam wave. There's a ship there, waves are coming from the beam side. There is a ship here, waves are coming from this side. So it will go like that, more or less. Okay. So I told you in hydrostatic case, you can afford to make mistake in aerial mass damping, exciting force. Okay, you can afford to make mistake. But then the point is that even if you made a mistake, situation is not dangerous. Unfortunately, what happened when you do this other extreme end, the ship behavior is actually opposite phase. That is, I mean, this goes like this goes like this goes like this. I mean, what I am trying to say that it goes opposite phase. So what happened? This is when the inertia dominates. The interesting part, interesting or unfortunate part is that where my situation is more dangerous, which obviously in this case, because you can see that if the vessel is bent like this, more dangerous because the deck is closer to the water than if it was falling. See, in this case, if you are standing here, of course if you make it long, you will not feel you are moving because your water is at same depth below you. But here you will see that your water is coming up, you are closing down. Water is coming up. When the wave is raising, you are going down here. So it is dangerous. Unfortunately, this happens when inertia dominates, and that is the case when you need to find out the hydrodynamic more carefully. So, in roll case it turns out that you cannot avoid hydrodynamics because the more dangerous situation arises where hydrodynamic forces are more important. So, whether we like or not mathematics, you have to have some estimate of hydrodynamic forces. That is what I want to tell here. Then I want to tell you another interesting thing about this semi-submersible. See, natural period in heave, say heave, is proportional to area of water plane and mass, okay, something like that. Now you see, semi-submersible, you cannot get away from a particular site, unlike ship, because it is anchored. It is anchored at one place. You are getting oil from there. Unlike ship, your bad weather comes, you cannot run away from there. Okay, so good or bad, it must be surviving. And if it heaves very much, you cannot dig oil. It must be small heaving. What you want to do? You want to reduce heave. So what you want to do? You want to make sure T heave is far away from that typical wave period. It is about 25 seconds. 25 seconds is equal to 20 seconds is equal to a wave of something like kilometer long. That does not occur. Mostly the waves that what is used in offshore as everyday wave is about 100 to 300 meter long. 8 to 12 second or 14 second period. 20-second waves or 25-second wave don't occur very much. So your idea is here that you design a structure so that its natural period is far away from the usually occurring waves. So it is like you make it 25 seconds. How do you do that? You can of course make the other side, that is not possible. So I made a mistake. This is proportional to 1 by, because omega is proportional to this. T is proportional to actually mass by AWP. See, omega is proportional to AW by M. This is ulta, opposite. Okay. So if you want this high, you have to make it low. This is exactly what you do. You make it low by only 2 circles or 4 circles. That's why they call column stabilize. Now what happened if you have this thing going out is small, you need mass, large mass. How do you get the large mass? So you put the large mass underwater, pontoon. So you put the large mass underwater, below water. So you have got your mass high, but you want AWP small, so you got a AWP small by just putting the one that is penetrating small. But there is a safety issue. You want GM to be more or less good. For GM, you need I of the water plane area high. How do you get that? All you do is that you simply make this away, because I is proportional to area into distance square. So you have small water plane area, but like a catamaran hull, you just space it out. This is exactly how this design evolved. The entire idea of semi-submersible is that buoyancy will come from there's a submerged part where it doesn't contribute to water plane area. Water plane area is by the smaller part, columns, and the columns are far apart to stabilize the body to get high I. That's why you call column stabilized. One more thing is there, that if you see the wave part, the pressure is always exponential. So if you have a small part penetrating out, the net force pushing out is much less. Exciting force is also reduced, because the pressure that comes here from wave, because it is much below, it is much lower. So so this is the entire concept of semi-submersible, that what you are doing, and typically it will look very interesting that in a typical ship, a typical ship omega versus heave, it will look like it goes high and then resonance goes like that. It goes more than one. A semi-submersible will go like that. Its resonance period is going to be, oh sorry, I think this will be high period. This will go like that. See, a ship would go having a resonance period high, but it goes up. But here what happened, it actually, resonance is somewhere here, but at the resonance the excitation is small. So although it is resonating, the motion is smaller than even 1. So you see it will resonate, but because exciting force is small, everything is small, it resonates, but heave is very small. This is an idea of this is a semi-submersible type, and this is a typical ship. Okay. Now this is where I am going to end this regular wave part, but the reason this I say that after all irregular regular is integrated connected, we will find out. We will see that how a vessel behaves in irregular waves is completely decided by how it behaves in regular waves. Therefore, it is very more important actually to solve this part than to solve the irregular wave part. So we will come to that in a minute. Maybe before that I want to say another interesting part. The typical RO, say roll versus say frequency. You may now, because it depends on encounter frequency, you can actually, this is a function of omega, v and mu. It turns out that by changing speed and changing mu, especially changing speed, you can actually change this. Supposing at v, at some v it looks like that. If you went to another v, it may look like that. Another v it may look like that, because what happened, changing v will change omega, will be making it closer to resonance. So there is a relation between omega, v and this roll. You see, this is an example of a container ship in waves. Okay. Now there is an exciting force coming. Now this particular wave condition, it turns out that at some frequency give force, some force. It is frequency dependent. Now obviously if you change the speed, the characteristic changes, and this is another thing that is important, because this is a typical phenomena that one uses. In this example it was actually 20 knot, this is 10 knot, this is actually 0 knot. You know, all of you probably experience more than I would, that if you slow down, normally it has a beneficial effect on motions. High speeds have larger motions because frequency is going somewhere, etc., and forces are faster, etc. So this also shows that the moving ship depends on frequency, but frequency depends on heading and speed, and therefore changing heading and speed, you can change the tuning. The resonance can be called that as if the ship has got tuned with the wave. That can be changed, and like that you can reduce the motions. Okay. So let me now forget this part. Now let me go to this irregular waves. This is very interesting, and I will request you to just get this once in your mind, and if you get that, you will find out that this concept is so interesting that it applies finding out not only motion, everything that you want in irregular waves. You want to find out pressure, you want to find out bending moment, you want to find out anything that you want, any response in irregular waves, the procedure will remain exactly the same. So that's why we need to sort of pay a little attention. Now you see here we have got, what do we have? If you take a ship in irregular wave, the irregular wave eta or t looks like very irregular. Okay. Now you have put your ship there and you want to measure your let us say heave or some response. Let us say heave. You measure zt. Zt also looks something like irregular, isn't it? See, if you have an irregular wave, then let us say you went down to irregular wave and you put a meter to measure how much it is heaving. So it will also look irregular record. What is our requirement is that given this, find this. We would like to have to predict this, given this. Why given this? Because obviously we have talked earlier how a C spectrum is defined. So I have a C spectrum, from there I can find out an irregular record, or in other words, let us say I have this. So I measured my input. After all, this is my, you can call this is my input. and this is my output. Why it is input? Because this is the existing wave environment. You can say this is the environmental disturbance that is existing. This is going to cause a disturbance that causes my ship to move up and down. So, I have to predict from here to here. Given this, find this. This is my objective, okay, and that is what is meant by how I find out motion at irregular waves. So, this is a very interesting part, and I will tell you how we go about it. See here now, first of all, look at this part, this irregular wave. What we had an irregular wave. I have to draw it slowly. Now, this what we did, we said that it can be broken down to a number of sine waves, this plus this plus right. This is what we have said earlier, isn't it? What we have said earlier, if you recall correctly, is that if there is an irregular record, we said that if you do a Fourier analysis or something, if you analyze that, you can assume that this is composed of number of sine curves of different frequency. If you add them up, you will get this, or if you have this, you can break it down to these pieces. Okay. This is what we said. In fact, we said this looks random, but actually there is nothing random about it. It is random, of course, but nothing complicated or confusing about it, because you can, on the assumption that they can be broken to many sine curves, the point remains how to break it down, and there are now absolutely standard mathematics, Fourier analysis, etc. to do that. This is irregular wave input. Now, I have to have an output. This is my waves, this is my irregular motion, say motion. This also, now this also looks something like that. So, this can also be broken down like this. Okay. This can also be broken down like this. Now, you see, oh sorry, I should have broken it down in the same frequency. Now, let us say that this frequency is, we have broken it down to a frequency of omega 1, this omega 2, like that, this is omega say I, like that, this is omega n number of frequencies. Here also I can break it down to the same one, omega n. Now, what happens? This gives me this input gives me this output. Now, I say that this input is nothing but this plus this plus this plus this, which I have done by spectrum. Now, what I do is that I find out that if this was my regular wave, what would be my output? That is, if this was my Z, A, what is my Z here? That means this by this for that frequency. That is what I have done. See, to get this from this was what I so far talked. That is how it behaves in a regular wave. That means, supposing this is my regular wave of amplitude A, 5 meter, what would be my wave? So, going from here to here this way is finding out response in a regular waves. So, what I do, I break it down to these sine components. For each one I find out if this was a wave, then what would be my regular, if this is a regular wave, what is my regular wave motion. So, I break it down to this, then add them up to go there. So, you see the algebra, this is a picture that you must keep in your mind. This is broken to this piece. So, this way, the next step I go from here to here, then next I go from there to upwards. So, you see I have this, break it down to these pieces. What is this breaking down? This is basically, this breaking down is algebra, pure what is this going from here to here? This is actually response in regular waves. A regular wave given, what is the output? What is this to this? Another algebra, just adding them up. So, you see, getting here to here is not so tough. It is actually in your mind very simple, because if I can break it down to these pieces, which I have done in a spectrum analysis, spectrum we say that actually it is nothing but this the broken pieces, then I can actually go from here to there. This part here to there is what we have done so far. That means, for each frequency I must find out what is my frequency response, actually that graph, that RAO graph, then add them up. This becomes so very simple. This is actually this is the point that has to be clear in the mind, because this is not only heave, this thing will appear for any response. Given a wave, find out the response, maybe heave, maybe roll, maybe pressure at a point, maybe bending moment at a point. What we are doing, given a wave, what is the it's okay. Given a wave, what is the response? Regular wave. I am trying to find out. Irregular wave is nothing but sum of regular waves. Okay. Each regular waves induces me a response, regular response. Add them up. So you break it down, go add them up. This is a picture that must be clear in your mind, because it is getting here to here appears very confusing, not correlated, as if it's very confusing. But it is actually the most simplest thing. This part and this part is pure nothing but algebra. Just you cannot make mistake unless in a typing mistake type. There is no hydrodynamic mistake. Entire hydrodynamic comes finding out in a single wave what is the response, which is what we talked so far. So you see the complication for us 95% is here to here, breaking and this. People call this and this as post processing, not even analysis in to this algebra, you see. So this is the picture we must keep in mind. Now I'll elaborate that more. Getting from here to here is RAO, that will elaborate more. Now let us see this same picture how I can do in a spectrum form. So I had this thing, you see, I said this diagram. See, this thing I said can be written down like a spectrum, S omega omega. After all, this spectrum is nothing but the representation of that. I will draw another picture of that. Now here I have got basically, this is my wave, this is my response. This also looks like that. This also can be written down like a spectrum, because any irregular waves response can be broken down to spectrum. This is a response spectrum I can call. This is omega, and this maybe response I can call it R omega, something like that. So what happened, going from here to here is actually going from here to there. In other words, I have this, I have to find out this, but normally I don't represent my waves by this way. I represent by a spectrum, standard it is a spectrum. So similarly, I don't represent by this way, I will represent by this fashion. So basically what would happen, I would be given this. Given this, I must find out this, which is same as given this, I must find out this. Remember one thing, this is a time, this is time. So what we are calling, given a time domain input of wave, find out time domain output of response. Same as given a time frequency domain input of waves, find out frequency domain input of spectrum. This is the kind of picture that we are looking at. I will there is a very nice picture in the reference that I will give you later on, but I will try to draw it here and see whether it can be sort of combined. This full thing can be combined in one picture now. Okay. This is a picture that we must remember. This may not come in one graph, so I will try to see. So here let me try to draw this in a very complex fashion. This is my spectrum here of wave, and each of them represents a wave. This is my omega, this is my S omega, these are all my etas, and when I add them all up, this plus this plus this plus this way, I have got. Okay, see, please understand this, what we have done. This is how I have done. See, there is a irregular wave, this one is obtained by adding this one, or you can reverse it. Okay, this is why I discussed before in irregular wave many times. There is an irregular record, can be broken down to regular record. Square of the amplitude, you put them here. This is proportional to amplitude square. Say amplitude square. Okay, you have made them proportional to, I mean, if you plot them here, a term proportional to amplitude square by delta omega, you have got this. This is what I discuss always. Okay, that means I have got, this is still the wave part. I have got this part, or to start with I have got this. This is broken down to this. frequency response which is squared, and I got this plot. Now here you see how this the relation will now come. This will, I have to draw here another one. See. Now see, this one now gives rise to a particular response. This one gives rise to a particular response. This gives rise to a particular response. This gives rise to a particular this. Exactly now I can take same thing, square of this amplitude and plot them here, and then I get here so called the response spectrum. So this has become now my so called omega, whichever way you like to look at, and if you add them all up, you have got this thing, and this is my S. Let me call omega. Actually, I can call it omega. Okay, let me call it omega right now. I will call this omega E part later on. That is another complication that will come. Okay, so this is a very, very interesting and very, very important way of looking at that. See how this diagram is more clear. You will see what we have done is that a record is nothing but sum of this wave which is represented like that. So you can see either way. This is time domain, this is time here. This time domain is broken to these pieces, all these are times, but it can plot them like a frequency domain here. Each of them gives rise to a time domain response, some you get a time domain response here. But if you plot the square of the amplitude, you will get this. What is this amplitude here? This is another thing that is important. What is the amplitude here? Let us say I am taking heap, so it is ZA is the response amplitude. Okay. What is this is here, this is wave amplitude. Okay, instead of A, I mean I can call this to be say wave amplitude. See here I have got square of wave amplitude, and here I must have square of response amplitude. Here I have got A square. If I call A as wave amplitude, here I must have that. I will come to the relation. See what we have to do, given these I must find out this, because when you do an analysis, you are not going to go down and measure. This would be when you measured it in actual case. But in our case what happens, see you have a shift there. Now you have, earlier I talked, you have a spectrum, ITTC spectrum. That means you are, somebody has given you this. They said that your significant height is equal to 5 meter, C state is 4. Therefore, you went to the formula, you have got this. Now you have to find out what is my significant heap motion. That means I must find out from this curve, and then again I will show you from there how I can get everything else. So I will be given this, I must find out this. But this is the physics behind it, the algebra behind it. As I again see that this to this, getting sum to this or here to here is algebra. How? Because this is a formula, nothing but a formula. Similarly, you will see that this sum to this is also algebra, because all we are doing is that for each frequency find the amplitude square and plot, you know, square of the amplitude over that period. You just plot that. Only this part is important. Okay. This picture should be very clear in the mind. This is the most fundamental picture. So this part to this part, that is ratio of this to this, give me amplitude square. Response amplitude operator. That is the response amplitude per unit wave amplitude. Okay, if this picture is clear now I will show you the way we go. Then now starting with that, I have got this S omega wave. I have to get from there, response spectrum, I must get from there. Now what is this proportional to? This part is proportional to response, say Z, response amplitude square. Square of response, because this one is proportional to wave amplitude square. This is proportional to that, isn't it? We have said that this part is nothing but half xi s square divided by delta omega. So obviously same notation, this spectrum is energy. See, it is, any spectrum is nothing but square of the amplitude of the signal. So here the signal amplitude was A, the wave amplitude. Here the signal amplitude was the response amplitude square. So this must be xi a square. How do I, supposing I call this to be, say, this particular term to be A and this particular term to be B. How do I get A from B? See, A is proportional to A square, amplitude square. B is proportional to Z A square. So I can say therefore B can obtain by A multiplied by Z A by A square. You see, now I mean, now this is an important part. See, A, this is proportional to amplitude square, wave amplitude square. This must be proportional to response amplitude square. Therefore, I can say B is equal to A, which is equal to proportional to Z square, because you see this, if you write that, this is A square into Z square by A square, that becomes A Z proportional to Z square. See, A is nothing but A square, so it becomes proportional to that. So you see this theory, if you see again, then I will tell you that S wave is nothing but equal to, or the ordinary of that is equal to 1 by delta omega half of A square, if you A omega square. Oh, let me write it again. S omega equal to let's say S omega at any some point S omega I at omega I. Let us say at some omega I, what is the value I am trying to find out? S omega I is given by our formula half of A I omega I square divided by delta omega. This is what I have done before, if you recall, that this part is nothing but square of the amplitude of the incident wave square divided by a that delta omega, that the delta omega has to be taken because the area becomes constant. Okay, this is what we have done. See this ordinate. Now again this we have to understand, how did we get the ordinate? We said the ordinates are proportional to wave amplitude square. Of course it is proportional, because if you just took wave amplitude square you couldn't get, so you have to divide by some kind of bandwidth delta omega. Okay, now I have to have this one. This will be my S say response, let me call it Z response. Okay, I mean I am talking of one particular response, Z omega. So this must be, this is S Z omega I, this must be equal to half of Z S omega I square divided by delta omega, because Z A omega I is the amplitude of the response of that frequency. See what it means is that this particular wave is a wave of this frequency with a certain height of A. What is this? This is equal to same frequency with a height of Z A. So obviously what you are plotting here is Z A square, what you are plotting here is A square. Question is, how do I get this from this? Now you see here, if you look at this, now I will have to go to the next, but please remember this formula, this one and this one, you will see that now I have to get this from this. See, I have to get this from this. How do I do that is the question we are talking. Okay. So I have to go to the next slide, and I will again show you that S omega I therefore is, we will write again this way, amplitude square omega I and S Z omega I equal to half delta omega Z A square omega I. Okay. This is obviously equal to 1 by delta omega A I square omega I by Z I, no sorry, Z I square omega I by A I square omega I into A I square omega I. Okay, this is equal to Z I square omega I by A I square omega I into 1 by delta omega A I square omega I. What is this? This is equal to S omega I, and what is this? This is equal to RAO omega I square. Okay, because it is Z by A, square of that. You know, you can call that if you want Z I by A I omega I omega I full thing square. Same thing, this part. This part is nothing but this. So you see what we are doing is that we can get the response amplitude, the response spectrum at a given point simply by multiplying the RAO square with this. Now I will show you this in a very more schematic way very nicely, that then you will understand this even better. So I have got here omega S omega, again I have got here, it looks like that, and I have got here omega into RAO, which is jet A by A, which will look something like. So you take any point here A, any point here B, you will get this as simple as that. You see, the algebra is so simple that it is embarrassingly, like embarrassingly simple, I may say. So what is this? This is my wave environment, because this is what has represented my irregular wave, how irregular wave looks like. What is this? This is my response in characteristic in regular wave, response characteristic in regular wave. So you get this and this added up to combine, what you get? Response in irregular wave. So you can see that what I showed earlier, that breaking down is a physics, but mathematically it is so simple. It is, all you do is that you take the spectrum, take this regular wave response, square that at that part, I mean if you do in a table form, just take number of them here, 1, 2, 3, 4, 20 multiplications, that is all, it's like Simpson's rule. So you can see that given a spectrum, given the response in regular waves, to find out irregular motion spectrum becomes equivalent to absolutely trivial algebra. You cannot make a mistake, to C equal to AB square, you cannot, nobody should make a mistake except in grade 2, isn't it? I mean this is as simple as that. So why I say this repeatedly is that it always appears very confusing that how will I get irregular motion from irregular waves, because both looks very complicated. I showed this earlier, maybe I'll bring. I mean when you see this sort of thing here, that irregular wave to regular wave, this here to here, this looks random, this looks random, how do I get from this to this? But this I have already found out, given a significant height I have a spectrum, and now if I have a spectrum, this to this transformation is that RAO. So given RAO, given spectrum, the other part is just one line multiplication. So you see, this part, this is environment. Oceanographers give me this part. Oceanographers give me this is what this gentleman is talking. We need the environment. This is what we do, how a ship behaves in one single regular wave. And most complex part comes here, because that is where you have to have added mass, damping, exciting force. If you have this, if you have that, getting this is piece of cake, so called, you just square it. There is nothing to it, and you have to understand this particular method is what we call spectral analysis. And spectral analysis is nothing but algebra. And interesting part of that, just like in our subject, that the important results are connected to how this graph looks like, etc., etc. That I will discuss eventually. The interesting, practically important results come out from here. But to get to this curve is a very trivial job, and the in-between path of getting this is the most difficult part. This is given, this is what you have to find from some source. If you have that, adding this up is no problem at all. Okay, this is something that we must basically realize, that here to here this part is absolutely straightforward part. I will talk little more, but the idea that has come here is that this is a random signal, energy of that should be also proportional to its amplitude square. So I must write something as amplitude square of the response, this is the amplitude square of the input, but then in response by input I already found out from here. So I can get this directly from here and here. Okay, and this is a, now if I want to do a table, I mean I will spend time only on this little bit. See, I want to do a table. So what happened? I have got, again I draw a small curve, this, and this is response looks something like that, and this, this is ABC. So this is S omega, this is say RAO, this is actually SZ. You make a table, omega values, okay, S omega values, number of them, say start from 1, 2, 3, 4 like that. Then RAO values, this is given from regular wave, this is given from environment. SZ omega I, just square of this into this. If you call it B is C A is A B square. So what time it takes, you can fill it, and then you plot that against this if you want. So you see the process is very simple, absolutely simple. Of course, we will pick up on that next class more. I mean, I will not do it today. Then how do you find out the things that you want to know? That is, you don't want spectrum only. You want to find out finally what is my average heave, or what is my significant heave. Is it good or bad? Supposing it is very bad, how can I tune it? How can I make it, like, now what happened? Typically what you will do, this remains constant for a hull, doesn't change, because given hull, at what given ship, at what frequency, how much it moves is constant. But this depends on weather type. Today's weather is like that, tomorrow is like that, day after tomorrow is like that. It is sea state dependent. So this part, the most difficult part, you do once for all frequency, freeze it. But then this procedure you can repeat for given environment. You will find out, for example, that this is my peak. It has lot to do with whether this peak match with this peak, because obviously you can make out if this is high, this is also high, you are squaring this into this, it will become very high. But supposing it turns out this peak is somewhere here, this peak is, this wave has a wave peak is here, my response peak is here, you square this with this, you will get almost a 0 here. This is what we will discuss, that is the most important part. This will explain to you why natural period is important, why a tanker behaves badly in typhoon but does not bother small weather, like 10 knot, 20 knots wind, you just don't feel it if you are in a 20,000 2 lakh ton tanker. But if you are on a 2,000 ton barge, you will feel the 20 knot wind equally badly and maybe than the other one. Okay, that is why small boats behave bad, because most of the time occurring waves are actually maybe 3, 4 meter, 2 meter like that, sea state 3 type. Even there it behaves bad. But a tanker you don't feel it, it doesn't get. But then on the other hand, if it hits a large typhoon type thing, it will behave badly. And it's all connected to this, which I will discuss at length. That is where the practical, implication comes in very, very much. That is extremely important of the practical part. Now there is one thing that is very important, that also I will talk, is that although I said this procedure is simple, there is one hitch here. This is omega, this is S omega. However, you see, this is, what is omega? This is, as you observe, the waves from a fixed reference point, because you have taken the record at a fixed point, but ship is moving. So although it's irregular wave, what the ship sees, each one, see, this one is broken down to number of waves. But the ship, this same wave would feel to the ship to be something else, because this omega will feel to be, this omega I will feel at omega EI. This omega I will feel as omega EI. Because supposing this is composed of, let me give an example, a 10-second wave plus a 12-second wave plus a 14-second wave. For the 10-second wave, when the ship is moving at 20 knots, will feel like an 8-second wave. The 12-second wave will feel like something else. So first of all, although I said that this has to be transformed initially to how the spectrum would be if you are on the ship, or as the ship would feel it. Okay, I will actually go to that next class, but I will just tell you why it is important. See, again, there is a ship here, it is stationary. Okay, there is an observation point here. The ship is stationary, and if you observe, the wave looks like that. Okay, but if you now move, okay, then same observation point, okay, is changing. So if you are moving now, then this same thing will get squeezed. Okay, So this is in kind of omega domain, this is in omega E domain. So first of all, if this looks like something like this should look little more spread because it will be stretched. Omega, each omega is supposed to change to omega EI. That means I have to first change the wave measured, that is spectrum given, which is for a stationary point, to an observer sitting on the ship. So there is a transformation there. Before I can start this procedure that I mentioned last class, before, see here I mentioned this to this, I have one step. I have to first change this to omega E. First I have to change that to omega E. So first from this to omega E, that I will discuss next class, but that is also algebra. But you have to know that, because after all, depending on how you move, this itself changes, and when this changes, this combination will cause a change. So this also has an effect on how you actually can tune, or just last thing is that supposing a ship is sea state 4, there is a peak wave coming at 10 seconds. Now if you are going at a different speed, that 10 will appear 8 seconds, and suppose your resonance is 8 seconds, then you are going to be badly hit. Change the speed, you make it 9 seconds, it will not be so bad. So we will discuss that in next class, the response part at more length. So today we will end it here. Thank you.
1951. A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape, and IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today, IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It
আকাশাদি হার মেনেছে লক্ষ্যে মোরা যাবো তাই দেশের তারে খাচ্ছি সবে আমাদের গর্ব ভাই যোগ কর্ম সুকৌশলম একে ক্ষেত্রে বর্ণ যোগ কর্ম সুকৌশলম आदर्शाय प्राणदास्मह्वयम् योगकर्मसु कौशलम् योगकर्मसु कौशलम् योगकर्मसु कौशलम्.
Indeed, in this Golden Jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.